Alright, hell yeah. So tonight we're going to read the theories of failure in mechanics of materials. And this is a really important topic to me because I had no idea. You know what I mean? So we're in material mechanics. This is the 9th edition for Hibbler. Let's see if we can get back where we were. Alright, hell yeah. And I even have this epic pen, so if I actually want to draw something on the screen, booyah, we got it. Anyway, so hell yeah. So why is this, something that I've never heard about? Well, it's a star chapter, so maybe you get done through this entire book and you have an idea of, how to get numbers on things. And the two numbers in material mechanics are stress and strain. And they're proportional, It's basically like saying, like load in pounds and a change in length. Those are, synonymous with, yeah. So, and anyway, and for materials, hell yeah, we're just gonna break this out. So for materials, they have linear properties where if you put a load, and you could just say this is force on this side, you're going to have a change in length on this side. Now this diagram, and then here's your XY axes. I need to get a tablet. Anyway, so and this starts to break off in this direction, and a lot of things can happen. It can go up like this and then break. This curve will start to tend this way and then go like that. But for the most part, we have a linear range. So on this graph, we're going to have a linear line, and then at some point, hey, we're just going to consider anything past this, and they're going to talk about that. Steel is going to yield for a little bit, and then start to do, well, it's only going to do one thing. It's going to yield, and then increase in strength, and then decrease in strength, and then break. But so they're going to talk about how steel yields, and you wouldn't want to get into that yielding range. Now, brittle materials will just go straight up and then break. They won't have any elasticity. And so, but for the most part, this linear range, is going to be, every material is going to do something different, but this linear range is going to be the same. And that linear range is where we get all of our strength, in that linear range. And so we have this as sigma. This is normal stress. Sorry, holy Toledo. Usually don't. I usually call strain stress. See, I get stress and strain mixed around so much. What we're talking about, this is the load, this is the change in length. Change in length is strain. It's this epsilon. And this is the stress in PSI. It's the load that you're putting on some sort of cross-sectional area. So hell yeah, this area would have a cross-section. And for sure, that length of whatever will have a, whatever you're changing in length, that will have a length. So, sweet. Cool. And so let's begin. I guess any material mechanics comes down to those 2 points. Is something can increase in psi, and then something can change in length, and we can have numbers on those. And the change in length is going to be represented by this epsilon because it's a change in length divided by the original length. And so this property is going to be the same for all materials are going to have a max. So let's go back to that graph. If this is the pressure and this is the change in length per unit length, and then this part is going to be force divided by area. That's the pressure. So if we have a straight bar, we're going to have some sort of force on it. Really need a tablet, but whatever. So you have some sort of axial force, and you have some sort of cross-sectional area. So this is three-dimensional, and you can see that if we do have an area, hell yeah, that's going to be our cross-sectional area. And so you get the same representation as pressure. You have a force acting on an area as basically pressure. Now the only thing that's going to be different, and we got to, there's another value that we're going to be taking a look at, because we're going to be talking about it a lot in this little section, is shear. It's when you have a force that way and this way. Two opposing forces that are trying to get this shape, this section, we're trying to get this section to go this way. You know what I mean? So that's what we're trying to do to that section. And we're trying to get this section, to go this way. So that's what we're trying to do to that section. And if we were able to do that, get those two sections to slide past each other, that would be the end goal for that idea. That's what we call, on that surface area, right there, that we still have that surface area in question, but we have two opposing forces, and we call this shear. So here, if we have two opposing forces, just two F and F, we can use that to get these two objects to do this, or we can use these two opposing forces to get this object. For sure, this will lengthen this object, but at some point, kind of the general gist here is that, we're expecting it to fail on that surface area. Like those two chunks are going to rip apart in that. And we're going to see that if this was steel, a lot of ductile materials won't just rip apart. If this is glass, hell yeah, it'll just tear apart just like that, maybe, just right on that face. But we're going to find that for ductile materials, they're going to fail probably at a 45-degree angle. And so we're going to have, some sort of 45-degree angle, and that's what we're going to... All right, so, man, that was a lot of intro. But I think it's good just because it's just like we're talking about material mechanics, what is it? And then so one more thing is I just thought that for materials, you have like a normal, this is PSI, this is going to be normal compression stress. It's pressure in compression or pressure and tension of that axial bar. And we have a number for this. We have a max number. So that's going to be this number right here, and that's going to be like max. And then, and then when we did the shear, that's still going to be, we say that's tau. And tau is going to be still that force, those opposing forces, or the force divided by the area. And just like axial tension is the force divided by the area. It's the actual axial tension or compression, and that's going to be sigma. So hell yeah. So we have these two equations. And then you have your strain. And you can have a max strain. That's just going to be, hey, the most you can change the length from the original length before you get out of that linear range. So again, if here is the stress strain graph, and again, you can think of this as change in length proportional or load and force. So this stress strain graph is proportional to these two things, and it's proportional to these two things. Anyway, let's just leave it at that. And so you get something like this. Increase the load, you're going to increase the change in length, is generally what's going on. We use stress as force divided by area, and strain as change in length divided by original length, because now this becomes, it doesn't matter how long our specimen is or what type of cross-sectional area our specimen is. If this is made out of steel and this is made out of steel, it's going to follow the same exact line on this graph. It's literally going to go through the same points on the graph, and then you're going to get to that yield. And so, so right here, right where you get to this yield point, right there is going to be your strain max. So this is going to be your maximum change in length per the original length you started with. So cool. So you're going to have strain max. And then in material mechanics, I just swear is just like, even going into a hardcore study session on material mechanics this last couple of months, is like, hey, any material, if it reaches these numbers, then you have failure. So that was my idea of failure. That's what we're going to talk about. But that's not true, because you could have a spherical ball and drop it into in the ocean. It can be at the very bottom of the ocean where the pressures are so great. Only like 6,000 to 10,000 psi, but that's psi's that, hey, might get up to some materials. 10,000 psi is all they can take, let's say. And so, but if you have some sort of material and you drop it into the ocean, you can have everything going on. Your change in length can be max. You can have the max compression where this thing goes beyond the linear range in compression. You can have a stress and a psi when you put something at the bottom of the ocean for that material that goes beyond this number, the normal strength. So that was the biggest deal that I kind of now realize, like that's important, and I think they should talk about that in a book way more. Is that like a lot of the Titanic materials didn't fail due to pressure. All the molecules are just equally closer together. That doesn't cause failure. Same thing with molecules getting equally far apart, especially if we're talking about this linear zone is such a tiny change in length that it would be a straight line, and even steel can sometimes increase by 30% before it's actually going to break. So it has a very ductile, even steel, 5 to 30%, but this usually 10%, 5 at minimum typically, but 30 at maximum. And then we're talking 0.2% for the linear range. That's, just as 30% is proportional, 30, this number 30 is a percent, it's going to be 0.3. So whatever the length was, multiplied by 0.3, that's going to be your change in length. Where this linear zone is 0.2. So as a percent, you're going to have 0.002 as this is the max strain for steel. So this is steel's max strain. And this number is pretty small, but you get a lot of strength out of, most of these materials are like, even though they act like springs, they're very, very stiff springs. And so the change in lengths are very, very, very small. All right, sweet. And so stuff at the bottom of the ocean, that's not necessarily causing failure. But if you have a bar and you put loads either direction, I'm just going to do that, tension or whatever, hey, guess what? Or let's do the opposite. Let's say you put compression on this bar. What do we not have that's different than the ocean? Well, this bar has, two other sides. What we're not doing is putting loads this way and this way, or this way and this way. So if we're not going to put in those loads, then it's not like something dropped to the bottom of the ocean. And therefore, like you can get other modes of failure. So, and that's the place where I'm at. At least I kind of get this idea that so in this case, yeah, you reach this pressure max, you probably got issues. You know what I mean? Because there's nothing else helping. But if you go and strap, you like get like steel straps, and you're able to somehow strap this whole thing together and put this compressive load on it. So this would be compression, and that would be sigma C. Poisson's ratio says that when you compress something, it wants to get fatter, it wants to get wider in all directions. You know what I mean? Or, it's going to get shorter in this direction. Like this is the this is the length of this thing after compression, but then it widens out in these other two. So this is kind of the x direction. We're going to call this the y direction, and then out of the page is the z direction. It's going to widen in both the y and z directions. That's a bad thing. I mean, that's why this stress is when you have something like a 2x4 and you do this, hell yeah, you can only get to this max compressive stress. So you run a bunch of tests for the material, and then you see that if you kind of have this axial loading, hey, you reached a pressure and compression, and then you saw failure. You know what I mean? You saw yield in steel, or in brittle material, you saw catastrophic failure at that point. And so again, on the graph, that's going to be right there. You're either going to see failure for brittle materials just right there, or some yielding that takes no extra load. You know what I mean? And then some extra load, and then it might come down and break. But right here, yielding is where you get this, where it's just like, hey, it's no longer linear, and it takes no extra load for it just to start pulling like taffy. And so for ductile materials like steel, we're going to call that, I'm going to call that failure. They call it yielding, but I think yielding doesn't sound like people are going to die. Where in hell yeah, that's kind of like steel's. I would make it synonymous with steel's failure point, because there's a lot of things where crap could go wrong if stuff starts yielding. Now it might be designed in where once this starts to yield, you have other structures that take up the load. Let's say indeterminate structures where, like one can increase by 30%. It's such a kind of a cool material mechanics perspective, where, and this graph is kind of fascinating. Sure, it yields. If it's the only thing holding up, like a semi truck, that semi truck is going to break those bonds and is going to fail. Well, it might increase in strength a little bit, but probably not. It's just going to, where if you have something like this that's just overly long connected, like a steel cable, this steel cable could lengthen by 30%. You know what I mean? So sure, it's in this zone. You know what I mean? But so it is. They're going to talk about ductile materials yielding, and so you have to consider, well, is that the only thing holding this up? Because if it will, you're just going to go to there. It's just going to lengthen and break. So right there is no different than right there if it's like literally the only member. But if other things are taking the load after that one yields, you know what I mean, then that one can still take this amount of tension. Like it's still in that amount of tension. The tension don't go to zero, you know what I mean? So that member still is holding that up. All right. So sorry about just I think doing an intro to material mechanics like every video is very important. So what did we learn from that? I wanted to talk about the bracing. So if we have all those metal braces around this, and we have this thing in compression, well, now it's very similar to that whatever's on the bottom of the ocean. If I have these pressures in 3 directions, due to these straps holding this thing together, more think of it maybe as a circular dowel or something with steel straps around it, hell yeah, then, it's the same, maybe sky's the limit, where, you don't have where this compression in max, where that gets maxed out, well, maybe if you're compressing it on all sides, you can actually go way higher than this. And not to say that this section will cover that, but just keep in mind that I was under the impression that if any point in this material sees a compression or a tension, just general, and that's considered the max number for that material, then hey, we got issues, we got failure, whether it's shear max, tau max, or whether it's the strain, the change in length max. But you can have configurations. Like I said, the bottom of the ocean is one that's just fascinating. Things aren't just going to break apart just because they're in heavy compression in all directions. And technically, and again, I'll say it one more time, try to, is just like if you pull out on something in all directions, because this change in length is so small, like this linear zone is just tiny, where sure, you could pull something in even a brittle material that would break at that point. I think if you don't quote me on this, but I think the analogy is similar. You could have a glass sphere that has a breaking point that if you're able to, pull on this sphere on both sides, it's going to break apart, the cross-sectional area. But if you were able to pull in all directions equally, I think that's just very difficult. Besides the vacuum of space, or just a vacuum in general, you can't. I don't think you can have outward pressure in all directions. I think it would be very difficult to simulate that. But I think it would be a cool experiment to even from like having a glass sphere that if you pulled, you would like tape. I think this would be one that I would want to maybe experiment with. Like tape adhere a bunch of strings, and then have a bunch of strings just in this direction, that on that side, and then this side of a glass sphere, and then pull it apart, and see what the force was, and then have strings all around it, and try to pull in all directions on that glass sphere, and this would be a difficult experiment to do because you would have to figure out all the tension on each of these and then see what the total was. And then, and then pull in all directions. But I think you could pull more. That force would be much greater if you pulled in all directions on a glass sphere before it breaks. And I think one aspect is that the change in length in the linear zone is so small that as long as you have this equal compression, equal tension, you can go beyond that without molecules, getting too far apart where they're just separate, electrostatically, I think. But don't quote me on any of that, you know what I mean? Okay, so hell yeah. So now we are just going to start reading this chapter. That's kind of what I wanted to do. I don't want to make two parts of this video, so... But damn, that was a lot just to. Let's see. Let's zoom in. All right, booyah. Yeah, might as well get as close as possible. Well, that's a little bit too close. All right, so let's read. And this is the other aspect of just learning. It's just like I'm gonna drink some water. But I don't want to do any of this. You know what I mean? I don't want to read this. And it's a fear factor. It's just like if I read this, I might not know what's going on. There's going to be aspects of this that I'm not going to know what's going on. So hell yeah, let's see if we can do this. All right, when an engineer is faced with the problem of design using a specific material, let's say steel, it becomes important to place an upper limit on the state of stress. So we talked about that. PSI, intention, compression, that defines the material's failure. This is just, I thought this was gold. I thought we were doing this the entire time. I just didn't realize. We did the Titanic analogy. Let's move on. If the material is ductile, failure is usually specified by the initiation of yielding. We showed that on the chart. Whereas if the material is brittle, it is specified by fracture, but that's still at the top end of that linear range. You know what I mean? It's still linear, 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 and then you reach a top strength and it fractures. These modes of failure are readily defined, and yeah, so those numbers are just out there. And here's why they're defined. If the member is subject to very basic states of stress, uniaxial states of stress, just pulling apart on something, compressing something in one direction. That's uniaxial, one direction. As in the case of simple tension, And that's the case. However, if the member is subject to biaxial, so even just putting, you know what I mean? So that was kind of cool because we kind of figured it out. So even if you just have this in compression, but then you put this in compression, so we said, hey, we have a number for that. That number is where this thing's just going to break. It might break at a 45. It's going to break, due to, shear, or even though you're just like, how's it going to break? That doesn't matter. Like, this number is when it's going to break if it's just uniaxial. And why is, and then what one aspect? No, I think the Titanic analogy is good, because when we compress on something in all directions, what happens? It gets smaller in all directions. Now that thing is just that size. Where Poisson's ratio says, if I compress in on this, it's going to fatten. It's going to get shorter, but then it's going to get fatter in all directions. You know what I mean? So it's going to look like that. And so, and if I pulled on it this way, well, that's just going to be even worse. Like, it's going to get even larger in that direction. And so potentially that's, so just, I think the Titanic analogy is good. I don't know, like, my intuition isn't very good to say exactly why, like, this would be worse, but, using the Titanic analogy of just like, hey, if you have compression on all sides, hey, you can do more. This thing could be higher. So let's just, hopefully that analogy holds, and if I actually put compression on this and start ripping it sideways, or in the Y and Z directions, hey, that's going to potentially, let's read on. Because these numbers in simple tension, I mean, still we still get a value for molecules or a little cross section. We do our little squares and we get these numbers. You know what I mean? And if they're past the max numbers for just simple axial compression or tension, it seems like we got issues. I can't imagine something's going to fail before you get to those numbers. So I think let me think about that. So reading through here, if I took a little segment and I always come up with numbers that are smaller, even after transforming them, because that was this whole, like, this chapter and the chapter before was like, sure, you found this and this and maybe this and this, but rotate it 45 and maybe the story's, way different. Like, the shear is just crazy. And so here there's no shear. You know what I mean? So that's the whole idea. But still, you know what I mean? Rotate your element 360, get these numbers. Compression and shear stress. So we have compressive stress and shear stress. And even same thing for strain. You have normal strain, and then you have shear strain. So those are your four numbers that probably have common maxes for materials. All right, let's read on. All right, sweet. So those modes of failure are very well defined for uniaxial stress, like simple tension. However, if the member is subject to biaxial or triaxial stress, the criterion for failure becomes more difficult to establish. And see, I don't know why I just want to put general ideas on things. I think it makes it easier, but those general ideas can be totally wrong. So it's just kind of fascinating, because I just did a general idea of just like, something's not going to fail if any of those numbers are less than these numbers. No, that's not right at all. So so I'm sure there's, because of what we just said, if you make a material in a situation that's leveraged, just you're pulling on it in the worst directions possible, maybe those stresses might be smaller, and it yields to still failure of that material. That would be interesting. All right. So it says, and just in general, the criterion for failure becomes more difficult to establish. In this section, we will discuss 4 theories that are often used in engineering practice. To predict the failure of a material subjected to a multi-axial state of stress. Yeah, so we're going to rotate in 3 directions, and so no single theory of failure, however, can be applied to a specific material at all times, because a material may behave in either a ductile or brittle manner depending on the temperature, rate of loading, chemical environment, or the way the material is shaped or formed. When using a particular theory of failure, and that's probably typical for steel. Like if you make steel like into tubing, man, I've had it just rip, very much. It seemed like it didn't give at all. It just tore, in a very brittle way, just based on shape. When using a particular theory of failure, it is first necessary to calculate the normal and shear stresses at points where they are the largest in the member. This is what you do, is you get those numbers, and it seems like that should be big enough. If those numbers are lower than the max numbers, that we got from axial tension and compression, or just normal shear, then we should be good to go, right? But that's why we have this chapter. And we're going to see, what's going on. Once this state of stress is established, the principal stresses, so any rotation. So you might have, a little element. It could you could have put the sensors on at a 30-degree angle, and you're going to find, maybe you find the strains. The strains relate to the stresses, and now you have the stresses that are doing something like this and this, and maybe you got some shear. Well, there's going to be some principal stresses where you rotate it to an angle, and hell yeah, like either 2 of these are going to be big and the other 2 maybe not as big, but you're going to have no shear, and that's going to be the biggest stress you're going to get, and also the smallest or the opposite direction stress, and those are your principal stresses. And so and those are going to be in normal compression and tension, and that's principal stresses. And so, hell yeah. So once we get those, since each of the following theories, and then that's the first step. It said you have to get those. Go to the place in the bridge or whatever where those are going to be max. Those are going to be your max numbers. Now we can talk about these theories. All right, booyah. So we have ductile materials. This happens with steel. When you pull on it, it doesn't just rip down the middle, just tear apart like this. It actually starts to slip and slide across 45-degree planes, and it could break at a 45. Ductile materials. Max shear stress theory. The most common type of yielding of a ductile material, such as steel, is caused by slipping, which occurs along the contact planes of randomly ordered crystals that make up the material. If we make a specimen into a highly polished, thin strip and subject it to a simple tension test, you can actually see these lines. And we can actually see how this slipping causes the material to yield. And these lines form, and it's not just, it's not just molecules getting farther apart, linearly. Which you would expect, maybe. If you drew lines on it this way, after pulling, those lines just get farther apart. It's just like, hey, that would make sense. But the appearance of these lines are showing, the diameter. This width goes in. So this width goes in, but it's because these lines are slipping across each other like that. All right, sweet. Alright, so we actually see how the slipping causes the material to yield. That's figure 1026. The edges of the planes of slipping, I don't get that, but maybe just in between. What does that mean? The edges of the planes of slipping as they appear on the surface of the strip are referred to as Luder's lines. I don't know how to say that. These lines clearly indicate the slip plane in the strip, which occur at approximately 45. So, yeah, my geometry is awful. I can't read that. The edges of the planes. Like, what would even be the plane of slipping? Is it if it did rip apart and you put 2 sheets of paper in between that rip, would those be like would that be a plane? 2 planes coming together? And so the edge, what the heck's the edge of a plane? Well, a plane would be, an infinite sheet of paper. But since we actually do have an object, is that saying that, heck yeah? So this is your into the board. This is your plane. That's your plane. And because the plane ends at the surface, the edge of the plane is the visible surface. Oof, I think I deciphered that correctly. All right. So these lines clearly indicate that the slip planes in the strip, which occur at approximately 45, I'm not reading this sentence right, but these lines clearly indicate the slip planes in the strip. That's it. Pause. And then these occur, which occur at approximately 45 degrees with the axis of the strip. Heck yeah. The slipping that occurs is caused by shear stress. Heck yeah. I'm not going to go over that, but yeah, that's what causes it. To show this, consider an element of material taken from a tension specimen when it is subject to yield stress. This is figure 1027A. So we have, this figure right here. So we're going to have to take a look at that. So this figure 20, so we have a Mohr circle, and then we have, it's shear stress. And so we're just going to pull on it in tension, and when we do that, it's associated with this Mohr's circle. And if we take this square, we're going to have compression this way. Tension this way. But there's no normal stresses in this direction, the x direction. So our principal stress is this. And when we rotate this, these get closer together. So this is the max. When this one, because this one doesn't go negative when you rotate it. You know what I mean? It might go negative. If this is a big positive number, hey, there's a rotation where this might become a big negative number. But also what we don't have on this element is any shear. So when we do rotate it, so if there's an element that is in biaxial stress, and you could say this is in biaxial stress, just the stress in this direction is 0, so it's uniaxial, but hey, work with me. So we have biaxial stress where one stress is 0 and this stress is a big number in that direction, and tension. We don't have any shear, so that is indicative of that when we do start this, that defines a principal stress. A principal stress is when you can analyze a little segment that doesn't have any shear. If it doesn't have any shear, you know for sure you have reached your principal stresses. So this is whatever number is max, and this is bigger than 0, and it's a max positive. It's in tension. This is it'd be interesting. Even just reading this is just like your principal stress is always the biggest one. So if this was in compression in a biaxial state, would that mean that your compression stress of 0 is your first principal because that's the largest number? The other number is negative. I'm pretty new to the Mohr circle, but I just know from this, you draw your circle where this is always your first principal. Even if this was at 0, because here's the axis, even if this circle is shifted over here, this principal stress could be 0, and then your max compression would be over there. And so that's exactly what I just said, so that's probably true. All right, so so this is a state where these are your principal stresses. So on the Mohr circle, we're at the biggest compressive or and in this case, it is a tensile stress. It's a positive, so that's the biggest tension. And then the other principal stress is 0 because there's nothing in that direction. That means when we rotate it, we can only get stresses in between those two. So you're never going to get a bigger stress than that, a bigger normal stress, but you will pick up shear. So, and we rotate it to 45, you get the max shear, and that's going to be right there. And on the Mohr circle, angles are double. So this is a rotation of 90, and it's always from your principal stress, rotating negative, well, the Mohr circle goes this way as in the positive direction. This is your positive shear stress. We have to draw a Mohr circle to relate to reality, and we do so by saying that this is your tension compression, this is your normal stresses, and this is your shear stresses. And this is the positive direction. So the negative y direction is positive. Or I mean, just you would actually just call this the positive y direction, just downward. That's positive. And this is the positive direction. And so if I want to get to the positive shear force, it's going to be this value right there. That's the negative shear force. It's the same value. It's just negative. But to get there, on the Mohr circle, we use the right-hand rule for angles. So if I'm starting, doesn't matter where I start on the circle, but a positive angle is going to be this way. So if I increase my angle, I'm going that way. So if I'm at this principal stress number 1 and I want to get to the positive shear stress, I got to go a negative 90 on the Mohr circle, but this is always a 2 times the angle. So that means in reality, I just have to rotate my thing 45 degrees. And we rotate it negative. So if, how would that work? I need to get let's see. So if I rotated this in the positive direction, it would be rotating that way. So this face would go up to there. So this face was my original X face, and we rotated it down 45. So that's that's probably more than this picture, more information than this picture explains. But hell yeah. So we can pick up a shear, and what we know is that shear is going to be max at a 45. And again, still don't lose sight of just the general that, hey, when we shear something in pure shear, this is going to have a max number for steel. When we compress something, and then when we tension something, we're going to get max stresses. So those are going to have a number, and these are going to be max. And so cool. And we know from, so Mohr circle isn't, yeah, this is fascinating, because this will say that materials will fail. I don't know exactly 100%, because we already know this. This is a common thing in material mechanics, that sure you're tugging on something, but you're also at a rotated angle, you're going to shear it, and still that shear has a max. But that still gets down to the basics, that if those numbers are matching these numbers, we got issues. So I'm kind of waiting for the point in this special chapter 10 where it says hey, that's not 100% the case, or we're just analyzing it to find these numbers. You know what I mean? I'm definitely not explaining that how I want to, but all right, we got to move on. And sweet. So yeah, so that's the figure. So what we're going to see is the maximum shear stress can be determined by drawing Mohr circle for the element, and that's by drawing the principal stresses first, there and there, and then we just know that when if we know our principal stresses, we know the radius. So yeah, if you know the principal stresses, you know the radius of Mohr circle is because this is the diameter. The difference between the principal stresses are the diameter. And hell yeah, so Moore's circle is just half that diameter, which is that principal stress divided by 2. All right, more water. All right, hell yeah. So that shows that max shear stress is that max principal stress. That's going to be the tension in the y direction divided by 2. Okay, so furthermore, this shear stress acts on planes that are 45 degrees from the planes of principal stress. So that figure in the C part shows the rotated element. And we get a max shear of sigma y divided by 2. What happens to our principal stresses? Well, at this point, they're the same. See how this stress becomes sigma y over 2, and then this max principal stress reduces to sigma y over 2. And so we're right at this point. This point is, a point on an xy coordinate system, and so that's what we get. And that's what I'm just kind of getting used to. I did a lot of videos on the derivation, algebraically, and the derivatives involved in getting the equations for this circle and stuff like that. And I thought that was very useful. And now I'm trying to pick through like the obvious, like that's why we do this, so we can see that our principal stresses are where there's no shear. So on our element, no shear. And the biggest and the smallest are the 2 points, and then that defines the diameter. And then so obviously when the shear stress is maxed, those principal stresses are the same. And so that's one way to think of it. See how this stress is sigma y divided by 2, and then the other stress is sigma y divided by 2. And depending on where the circle is, I mean, they could be the same 2 negative numbers if the circle's over here, or they could be the same 2 positive. They're always going to be the same, but just know those numbers could be the same, and both be positive or both be negative. All right, hell yeah. So let's see. All right, and so those so 45 degrees. Furthermore, this shear stress acts on planes that are 45 degrees from the planes of the principal stress, and these planes coincide with the direction of Luder lines shown on the specimen, indicating that indeed failure occurs by shear. Using this idea that ductile materials fail by shear, in 1868, Henry Tresca proposed the maximum shear stress theory, or Tresca yield criterion. This theory can be used to predict the failure stress of a ductile material subject to any type of loading. The theory states that yielding of the material begins when the absolute maximum shear stress in the material reaches the shear stress that caused the same material to yield when it is subject only to axial tension. All right, so there it is, and I need to read it again. So that theory states that the material will yield when the absolute maximum shear stress in the material reaches the shear stress that causes the same material to yield when it is subject only to axial tension. Huh. Okay. All right, so we're, I feel like that statement's like a redundancy. I don't know how to pick it apart. I'm just going to read it one more time and then move on. But I'm not going to pick up anything from it. The theory states that yielding of the material begins when the absolute maximum shear stress in the material reaches the shear stress. Oh, okay, so yeah, got it. The absolute maximum. So this also is the crazy thing about material mechanics. It's just like, well, if I pull on this is a bar, it's got areas, it's actually in real life, we got tension on it, I can put some gauges on it, I can just know the load, and I could actually find this number for compression. But let's say I put strain gauges on it, and I get the values at a 45, and let me just see if I can say this in words, because I still just think it means something. So let me just simplify it. When we do analysis, in whatever way possible, we can figure out the maximum shear stress that's happening to that bridge or whatever object. You know, we can find that number, and we're going to compare it to the maximum number that, well, that's the same thing as that we would always do. So I'm confused at this this chapter on theories of failure, on how they would just diverge from just the common sense of being like, so I'm sure there's something a little bit more in this sentence that I'm not getting. But in general, you know what I mean, if I could go to every location on this and figure out its max numbers, like rotate the element, I mean, that's what we've been doing for Mohr circle, and get the max numbers. Those max numbers can't exceed the numbers that we get from experiment. And I think now I'm understanding that we get our shear numbers. So if we're going to actually get a value on shear for a material, I think we do this. We just pull it apart. We pull a material. I'm confused at why this isn't just a tautology, or you know what I mean, like, is this what it's saying? Is if I have a ductile material that I know is going to fail in shear because I see the Luder lines and it fails at 45s, or at least yields. That's the thing with, we have to say failure is yielding, where it's just the presence of getting nonlinear. Then the second that happens, hey, we've called it for that material, maybe, you know what I mean, from that perspective. Even though it could, like I said, it can yield 30% and still maintain its strength, but it's just past that linear zone. Most things aren't designed past that linear zone. And so we pull on something, we get that value. And then I still think this absolute maximum shear stress just means that we do our equations and get values for that max shear stress that we're observing. And if it's larger than this test scenario where we pull something in tension and it starts to yield at a 45, then you can't pass that point. That's the point where that's yield in this case. That's failure. Yield due to failure due to yielding. All right, hell yeah. So we got to the first part of this that, you know what I mean, I have a little question about, and it's not fully fleshed out. All right, so therefore, to avoid failure, it is required that the shear absolute max, I'm confused on this, in the material must be less than or equal to the normal stress in the Y divided by 2, where the normal stress in the Y is determined from a simple tension test. Oh, okay. Oh, you know, this is very fascinating, because if we run a tension test, oh, okay, yeah, I'm failing to see that this shear, this equation is a legitified equation, that the max shear is equal to the compression divided by 2. And, yep. Okay. So, yeah, I can buy that. It is so to avoid failure in shear, the material must, therefore, to avoid failure is required that when we design the shear, the maximum shear you know, if we run the equations on all aspects of a bridge or whatever thing that we're trying to make strong, no point. No analysis of a little cube chunk of that thing can have an absolute maximum shear that is more. It has to be less than if you just pulled on the darn thing in a tension test divided by 2. In just the normal tension divided by 2 for that material. Okay, fair enough. And this tension divided by 2 is where the material starts to yield. Yielding is due to the 45-degree planes, due to the Luter lines, but those lines appear because of yielding. Everything else, those lines don't appear if you're in the linear zone. So we are going to talk about that just for a little bit, because on this graph, if you're in the linear zone, and it looks like this for steel, and this is your yielding, where there's no more load that causes that. If you maintain this linear zone, you go up to here. You know, what happens if you go up to here and then back off all the load? You come right back down to here. Every molecule goes back to the same location. So if you have, molecules here that you know their location, lines here that you know their locations, and then you tension this to where, heck yeah, it tensions all the way out to here, but this is still within the linear elasticity of the material. So you're going to pull it this way, and then you back off that tension. Everything just goes back to the same, every molecule goes back to the same location. And I think that just can't be understated. It's very fascinating. I mean, literally, like molecule for molecule, the same locations. I mean, that also is a testament that this change in length per initial length, which is called strain, epsilon, is very, very small for that linear zone. It's incredibly small. That's where most of the strength comes from, though. And, all right, sweet. Why did I mention that? Probably this little equation right here. Oh, because it's the one is saying the other. When we run this tension test, that tension test will yield, and we can see that from the graph itself. You know, you can see where that graph's happening, and then and you get this value for normal compression just because you are pulling on a specimen, like in a machine, and you're knowing exactly how much load. You know what I mean? You know how much force you're putting in. This thing has a cross-sectional area. You know that area, and then so for you know the stress. You know the tensile stress is going to be force divided by area. So with the machine, you're increasing this number, and you got a gauge on it. And you're seeing this, and you're getting this graph to plot. It's a straight line, and then all of a sudden at some sort of load or force divided by area, it starts to yield. And so a very simple tension test is getting that number, and we would call that sigma T for tension max. You know, I mean, that's going to be your max tension, and here we're calling it sigma Y just to show the direction. Because yes, most of these tests will be done in a vertical pulling machine. If this is the specimen, they'll pull it vertically. Doesn't matter if you pulled it vertically or horizontally. But sigma Y is that term that they're using. So, alright, so that was kind of the first little place where, you know, reading textbooks, I feel like I came into a hiccup. It was something I didn't know. So that's the amount of time that I wanted to spend on that section just to just kind of figure out what they're saying. All right, hell yeah. So now let's read more. So it says, for application, we will express the absolute maximum shear stress in terms of the principal stress. Okay, so the absolute maximum shear stress in terms of the principal stress. So if we know the absolute maximum, let's just read on. I think sometimes you'll have questions, but then they'll get explained. That's the whole point, right? So the procedure for doing this was discussed in section 9.5 with reference to the condition of plane stress. That is, where the out-of-plane principal stress is 0. So we have this where we have stresses in the y, no stresses in the x, and the out-of-plane is the z-plane. If this is the x-axis, this is the y-axis. So hell yeah. So on this is your x-axis, this is your y-axis. And then if you do right-hand rule, if I put my hand in this and roll my fingers up into this, you know, palm facing up, and then fingers, because that's how you roll your fingers, my thumb is pointed in this direction, so this is the positive z. And we don't have any stresses in the positive z. So that's kind of what they were saying there, just a little visual. And it says when we don't have that, what we get is also another circle to form. This circle was formed because we could rotate it about this axis. And we have, this is our principal stress, number 1. This is principal stress, number 2 is 0. When we rotate it, these are going to even out. That was the whole point of rotating it, where, hey, these stress, the normal stresses in that direction are going to be equal to that direction. So the same thing, we're going to take, and this thing is a cube, never forget that. And all we did was rotate the cube 45. So now the cube looks like this, and it was now rotated 45. What we're going to do is rotate the cube this way. And I think mentally that can just be kind of tricky. It's like sometimes it's like, well, how would I draw that? Well, the face comes down to a 45, and then the other part, you know, so now we kind of see the face. That's kind of what's happening when we rotate that this direction. And when we do, this force is no longer going to be max. It's just going to be just half. And then we're going to pick up, so in that force is, you know, on both sides. And then so you're going to get half that, sigma y divided by 2. And so that's out of plane rotation. And I can rotate this element. I can also, so in plane rotation it was rotating about the x and y. I could also rotate it about this is the y. So if I have my axes and I have this little box, just the general way to rotate it would have been to rotate it this way by 45, negative 45, right? But whatever, 45 degrees. And that's rotating about the z-axis. If you put an axis right here, this is how you're going to rotate it. So it's rotating in the xy plane, we can say that, and it's rotating about the z-axis. So tipping forward, you're like, okay, if it tips forward, it actually rotates about this x-axis, and it's rotating about the yz plane, you know what I mean? And then you could also rotate it another way. So that was, the first one was saying this is the axis, this is the axis. And so sometimes it's easier to see, hey, if this is the axis, because this one's, I don't know why that one's hard for me to see, but I can rotate it this way, you know, just kind of horizontally spin it like spinning a block on a table. And I can spin that 45. Nothing changes there though. So yes, so you could do that if you had biaxial, but because this stress is 0, your principal. So I could say this box. Sure, this is a big number. This is 0 in that direction, and then out of the page and into the page is also 0. So when I rotate it about this, you know, about the y-axis, but just rotate it just horizontally, hey, these are my principal planes, so more circle still applies. Like, I can come down here and just say my principal stress is 0. You know what I mean? Because I have 0, 0, 0, 0 in these directions. So the biggest number is 0. The smallest number is 0. And so here's principal stress number 1 and principal stress number 2. And the difference between them is the radius. There is none. And so there is no shear. And more circle is just a point. So that's why that's really hard to pick up, because especially in these textbooks, they really don't, I don't think they spend enough time going over the geometry. You know what I mean? Because I just even think rotating something in a different direction is just after you've spent just like an eon going through all the algebra. That was the craziness. You go through all the derivations to get your equations, and then they're just like, oh yeah, and we could just rotate it about the other axes. And you're just supposed to instantly, light bulb goes on moment, and it's very difficult to see. But hell yeah, so you are going to get an out of plane that's going to be rotating towards us. And so again, this cube kind of looks like this. If we rotated it towards us, now it really looks like this. Sorry, I didn't draw it. But yeah, it's rotating towards us. So this face is now rotating towards us, and we got a 45-degree angle. Alright, hell yeah, we're doing pretty good for me not wanting to make this video. I just know most of my videos are like 2 hours long, and well, I mean, that's just it's the time you want to put into studying. And it's just like, I just didn't want to read through this once, because I feel like I need to keep up with it, and that requires a lot of mental strength. So I'm going to grab some more water. Alright, so yeah, plane stress, out of plane. So out of plane principal stress. Let's just read this whole thing. Oh, excuse me. Oh, bummer. Alright, so for application, we will express the absolute max shear stress in terms of the principal stresses. The procedure for doing this was discussed in section 9.5 with reference to a condition of plane stress. It is where the out-of-plane principal stress is 0. Wait, the out-of-plane, yeah. Oh, yeah. So we have, we have this stress. You know what I mean? That's an actual number. And then in the z direction, that's, out of the plane of the xy. Biaxial stress is xy. That's going to happen in the xy. But out of the page, out of the plane, hey, we don't have any stress, so if we rotate about that, we just talked about that, because when those two numbers are going to be the same, your shear is going to be max. Cool, so out of plane stress. That is where the so your out of plane principal stress is 0. If the two in plane principal stresses have the same sign, they are both tensile or both compressive, then failure will occur out of the plane. Oh, so this is interesting. So we need to look at this. So if the two in-plane principal stresses have the same sign, they are both tensile or both compressive. And this is fascinating, because it really requires you to look at Mohr's circle. Because if but this is going back to the Titanic analogy. Like, if I drop something in the ocean, I have the same thing going on all surfaces. Whether it's tension or compression, doesn't really matter. I really don't even think. And there's a point where you pull stuff apart, for sure. The molecules get far enough apart. The electrostatic forces are overcome. But I think when it comes to linear elasticity, I'm going to go out on a limb on this, because it's linear. And electrostatic forces due to electron charges are fade with the distance squared. That's not what's happening when something goes from linear to nonlinear. It's more of molecules. I don't know. I'm just gonna say it at that. I mean, it's the same thing that gravity, is going to be the same if you fall off a cliff on Everest as at the beach. You're like, why is that? Well, it's going to be slightly different, and so there's just distances away. The distance between two molecules of steel are just hella far, and the distance that they can actually move is still 0.2%. It's still very, very low. Those distances are very, very small. So that's why it's fairly linear. I don't know if that's exactly why it's linear. Anyway, so hell yeah. So when we have this in tension, if I had axial tension this way as well, we get into that Titanic state. And I think it's easier if you say that we have compression in the y, and then compression in the x. Then you get kind of like that dropping something in the ocean. Like, it can just take a lot more. But then in the out of plane, you don't have any. And so when you rotate it out of plane, it's going to be, those two numbers are going to be the same. Once they're the same, you get the max shear. Where if this number is like 10 and this number is 10, there's no difference between them. If that was the case, if these two stresses in the y and the x direction are the same, then you just go to Mohr's circle, and it's the same thing. Instead of being at 0, point at 0, 0, your principal stress 1 is right there. Your principal stress 2 is also in the same location. You don't have a Mohr circle. I mean, your Mohr circle is a point. And so you don't pick up any shear. Also, if this is 10, let's say this is 10, and then this is 5, like right here to 5, then your Mohr circle, that's the diameter, your Mohr circle is smaller, and then that's your max tension. And so, but if this is 10, and this is negative 10, negative 10's over here, that's going to be the second principal stress, because it's smaller, and our circle is going to be out here. That means that their shear is going to be twice. Our shear is the radius of that circle. And it's saying that only in the case where this is a positive and the other one is a negative, where your biaxial stresses are positive and then negative, or negative and positive, or different signs, that's the only time where that shear is going to dominate. But if it's not, if these are 0, 0, so our biaxial stresses are a number and 0, you would call that the same sign. Well, no, that's when it's going to be the same. It's if you actually do have biaxial stress, like this number is a value and this number is a value. You have to see if they're the same, positive, 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 somewhere, our circle's smaller. If they're both negative, 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 our circle is smaller compared to having one of these be even if they're both negative, like one value is going to be larger than the other, and that's going to be principal stress number 1. So let's just say this is a negative 10, and the other one is a negative 5. So we got compression of 10, compression of 5. That's kind of like the Titanic situation, but what we don't have in this y direction is any stress. So when we rotate this, these two numbers are going to go to the midpoint, and our shear would be 5 if we rotated about the out of plane. Or if we go back to saying this is 10 and this is 5, negative 10, negative 5, the difference between, so let's go to negative, and negative 5 would be the bigger number. So negative, let's say this is negative 5 and then negative 10, and then here's our circle. All right, so what's the radius of that circle? The diameter is negative 5, negative 10. The diameter is 5. The radius is 2.5. So that would have a shear of 2.5 when we get negative, negative. But if this face has 0, then I have negative 10 and 0, and the halfway point between those is 5. So if I did negative 10 and 0, 0 is the first principal stress, negative 10 is that stress, and now my circle just doubled in size, and the radius of that circle is the max shear. All right, sweet. All right, hell yeah. So booyah. And, I don't think anything out of the ordinary is going on here with this theory of failure. This theory of failure is just saying, hey, you got to rotate your element in 360 directions. But yeah, I'm chill with that. That's nothing out of the ordinary when it comes to, you know what I mean? I was thinking, I guess, I don't know. You know what I mean? I guess just the fact that, yes, out of plane rotations are going to give, might cause a bigger number. And so, but yeah, so the whole point of material mechanics is finding the stresses in the pressures in an object, whether you rotate them, right? I mean, that's why we're in this chapter. And once you get those numbers, then you compare it to just and that this is at least starting that process. That's why you're comparing it to just, this really is defining max shear for Yeah, so now I'm confused of how shear actually gets determined. I mean, we're still with ductile materials. This little section is just for ductile materials like steel. But we're showing that those ductile materials will develop those 45-degree Luder lines. And cool. So let's read on before we just lose our mind. All right, so cool. So if those two in plane, the XY principal stresses, here we have, a number and 0. But if those numbers are the same sign, they're either both tensile or both compressive, then failure will occur out of the plane. All right, hell yeah. Equation 913. We're in chapter 10, so that's, but yeah, that's the equation from 913. That the max shear will be the principal stress divided by 2 out of plane. Because the in-plane principal stress is the difference between the two principal stresses. That's the diameter. The difference between these two numbers is the diameter of the circle. The radius is the max shear. So that's what we have right here. But if the out of plane has no stress, then this number is the out of plane. So this number is going to be bigger if this is a positive and then this is a negative. You know what I mean? If this, let's see, if the two in-plane principal stresses have the same sign. Oh, yeah. So if this is positive and this is positive, tension and tension, then positive minus a positive will be a smaller number than just that original. So yeah, okay, hell yeah. All right, so using these equations, the maximum, equation 1026, let's see, did they write an equation? There's 1027. Oh, here's equation 1026. The shear max is the normal compression divided by 2. All right, using these equations, equation 1026, the maximum shear stress theory for plane stress can be expressed for any two in-plane principal stresses, sigma 1 and sigma 2, by the following criteria. Sigma 1 is, if the principal stress number 1 is equal to the axial stress, and principal stress number 2 is equal to the axial stress, and principal stress number 1 and principal stress number 2 have the same sign. Oh, so it's the absolute value of those. Because they both could be negative and they could both be positive. I guess this is the equation. So what is this saying? Using these the maximum shear stress theory for plane stress can be expressed for any two in-plane principal stresses. I'm not fully getting this, but whatever. So hell yeah. So then we have a graph of the maximum shear stress. Yeah, why is this like the take-home point and it's not registering? Anyway, let's read on and see if we can come back to that. No, that's it. So a graph of these equations is given by the figure. Why am I just missing out, man? That's crazy. We kept up all the way to there. Using these, the maximum shear stress theory of plane stress can be expressed for any two in-plane principal stresses. So there's an in-plane principal stress, and there's one. Sigma 1 is y, sigma y, and sigma 2 is 0. Is this saying that they're both equal to sigma y? Yeah, so if principal stress number 1 and principal stress number 2 are both sigma y, and have the same sign, oh, this is interesting. I think I'm kind of getting it. You know what I mean? Because they're... Oh, man, I almost need to take a pause. I don't want to read another one of these. Because I'm about done. So, yeah, we did it. But, damn. So let's say we just have this. This is what's happening. Just like a big number here, no number there. Our max shear is just going to be sigma y divided by 2. I'm just confused why this doesn't have a sigma y divided by 2 in it. You know what I mean? Or a shear. This is an equation for 2 principal stresses. If we know the 2 principal stresses, I might as well just read this. So yeah, this is graphically what's going on. A graph of these equations is given in this figure 1028. Clearly, if any point of the material is subject to plane stress and is in plane, and its in-plane principal stresses are represented by a coordinate sigma 1, sigma 2 plotted on the boundary or outside of this hexagonal area, the material will yield at the point and failure is said to occur. So cool. So let's look at this point right here. This is where sigma 1 is a positive number, and sigma 2 is 0. So this value right here says sigma 1 is a positive number and sigma 2 is 0. Sigma 1 can equal sigma y. And sigma y is the axial stress that is causing those Luder lines. Yes. Oh, yeah. And then, holy Toledo. All right, so my bad. This is not the y direction. After all of that, I kind of, this is what I love about videos. I guess one of the subscribers is just like, I don't get why you love that, making mistakes. I don't know, because it's just like, it's like, now I won't make it again, maybe? No, you'll make all the mistakes again, and you just keep getting better. But this is yield. That y is due to what the hell we were just talking about the entire time. We're dealing with ductile materials. Their failure occurs at yielding. And failure with air quotes. Like, obviously, some things can yield and still maintain their strength as long as they're, kind of redundant, I guess. But yielding is what we're going to cause failure. If you get past, things in the yield state, you overloaded it. And so this is sigma yield. This is the, and this is synonymous with force. This sigma is equal to the force, force divided by area. So the force is the tension. So you could say sigma for this is the tension divided by the area. All right, hell yeah. And cool. So this is that yield. And so that value and is also, this is why I kind of just like max, I like to do this. I think this just registers so much better because look at this. So if you do the word max right here, and that's for material mechanics, I would just write your own words. If yielding is the suck that happens and people will die, then just call it max. You know, it's like even just having a y there, I confused it just with the stress in the y direction. And so that's really interesting. Where, I mean, this whole time we're calling this max, shear absolute max. And what, yeah, so those two equations now make sense. So when this is 0, you know, but when you just have uniaxial tension, hey, this is 0 and the out of plane is 0. So here's going to be your max. It's just going to be, and this is sigma 1 minus sigma 2 divided by 2. Sigma 1 minus sigma 2 is 0. So there you go, you got that. But if I do have this in the positive direction, you know what I mean, that's like the Titanic, it's going to be stronger. And so I'm going to have sigma 1 divided by sigma 2. It's not going to fail in that plane. But out of plane, this is also 0. So we have sigma 1 minus 0, and it's going to be the half. And then so that's going to be this equation. And when it's opposite, if I'm pulling this in tension and I'm pushing this in compression, let's go back to more circle. So this tension is going to be positive, sigma 1. The other principal stress, if it's in compression, is going to be out here. Let's just say it's equally negative. That circle is going to be huge, and you're going to get a much bigger shear stress. And so that's sigma 1 minus sigma 2. So sigma 1 minus sigma 2 gives a bigger value only when those two signs are opposite. If this sigma 1 is positive, this sigma 2 is negative, big circle. But let's say this sigma 1 is positive, sigma 2 is also positive, small circle. Where the out of plane, you're going to have sigma 1, and then the out of plane stress is 0, that bigger circle. Cool. So yes, so this is the yield, this is the max strain. And yeah, so sigma 1 right here is equal to sigma y. You know what I mean? So if we have this scenario where this scenario occurs when we just have tension in one direction, out of plane is 0 and biaxial is 0, and so cool. This is going to be the max stress. It's going to be equal to the principal stress, and in this case, we're saying, yeah, that's the other thing. Let's do this. Because in material mechanics, you don't have to put this subscript max. I could just, this is the worst. When you do a problem and you're just like, hey, subscript allowable. You know what I mean? This is always a good subscript because, hey, maybe your allowable is a factor of safety of 10. And, or just if you hardly load something, this is also a good subscript. Just, I'm just going to make it up. I've never done this one. But just load. You know what I mean? You could say sigma or tau load. And so just know that you could put a load of 0. You could put a load of 1 pound. You could put a load of 1,000 pounds or whatever's. And then so this value is going to be linear because it's proportional to the load. So just never kind of forget that. And yeah, so in this case, we're going to have tau max is equal to, yeah, I think it would be better to do this. Tau max is equal to sigma max divided by 2 if this is, if this, you know, because if we have biaxial stress, this is the max shear if this number is the same. If this is a positive and this is positive, then these two numbers, the average between them is small. So tau not max. How about just that? You know what I mean? Because you're taking the difference between two positive numbers. This is positive, you get a smaller circle. And so this equation is if those numbers are either positive, positive, the biaxial stresses are positive, positive, or negative, negative. This equation is when those axial stresses are positive and then negative. So this is the opposite of the Titanic. You know what I mean? Titanic is where you get pressure on all sides. Here, I'm pulling apart and then pushing something together. So this is, these two numbers are going to be additive. This is going to be a positive minus a negative. So it's going to be minus a negative, it's going to be adding. So we're going to get a bigger number here. And tau max is going to be related to that bigger number. In this direction, we have 0. You know what I mean? So our out of plane is not the plane of failure. Our plane of failure is in plane. All right, so this is pretty sweet because we got to the point where it's just like, yeah, it stopped making sense for me, but now I figured it out. This is the yield stress. So yes, and pulling on something and pushing on something is going to be the same, eh? Because they're doing the absolute value signs on these. Now for steel, that's the case. And I think it's the case for steel because shear don't really care what direction it's in. Oh, so I'm learning something here. I think that is a really cool tip on the fly. Is that primarily why with ductile materials? I mean, obviously, like rock is way stronger in compression than it is. Oh yeah, so that's a good one to talk about. Like rock is hella strong in compression, but it just makes sense. It seems like any material that you compress, like why would it fail? The molecules are just getting closer together. But if you think of the molecules just like bunch of balls, like a ball pit, and you push on them, like stuff's gonna happen, right? You know what I mean? Stuff's gonna squish out the side. So obviously that's also the Titanic. If you're pushing on the ball pit and things are allowed to push out sideways, that's not the Titanic. Titanic is where everything's getting pushed in equally on all sides. Hey, that ball pit's not going to go anywhere. So I think that's fairly decent little analogy. And I've forgotten what I was talking about. Yeah, so if it's negative. So if this is in compression, like why is that going to fail at the same as tension? Well, is because if you I guess it makes more sense to push on the ball pit, but same thing when you're pulling something apart. Like this thing is just made of round little electrons, let's say, and the tendency to slide past one another is what's causing failure with ductile materials. They don't so that's helping me like really reiterate the fact that ductile materials that can have the ability to yield will yield along planes of shear. And those planes of shear don't matter. Negative shear and positive shear is about the same thing, you know. So it really doesn't matter if it's in tension or compression. I think there's a lot of things that I'm thinking that are making sense mentally, but I'm probably not gonna be able to put the words on it. But hell yeah, I think that kind of explained it. Negative shear. If the shear arrows go the other direction, it doesn't matter. It's still same failure. And so you're going to get those arrows to go the other direction if you just push this in compression. I think that's halfway well said. That's probably the idea of these absolute values. So if my principal stress, if this circle is on the other side, if it's 0 and negative and we're in compression, if I just have axial compression in this direction and nothing in this direction, the circle is this way. My principal stress actually in this in-plane direction is my first principal stress at 0. That's what got me tripped up a couple weeks ago. is that your principal stress is always the largest number, even if your other one is a huge negative number. So that circle is going to be there, and the radius would be your max shear. And so yes, if these are either negative, then, and I think this one is the only one that would need, oh yeah, so I guess they both, it makes sense if this one has an absolute value, because the principal stress, the yield stress can equal the second principal stress if this principal stress is negative and has the larger value. Oh, whoa. So, no, let me read this equation. It says that these two have the same sign. So let's go, let me get some more water. Yeah, this is where like reading directions is good. So let's just have the scenario where this is negative and this is negative. The yield stress will happen. I don't like this equation because it's like I think it's either or, you know what I mean? So if they have the same sign, it's either this equation or this equation. So I think mathematically, you know what I mean? I wish they just explained like either or, because we just went over the scenario where if these are both negative, then the principal stress number 2 is the one that's most negative, and that's going to be the biggest number in compression, and that number is going to be the same as if you're pulling the specimen in tension. So hence the absolute value. So therefore, sigma 2, if it's a big negative number, and the other one is also a negative number, we're going to have, and this is associated with out of plane shear, because we're not taking the difference. If you took the difference between two negative numbers, you get n divided by 2, you get a smaller number than just this bigger number divided by 2. And the absolute value of that. So, hell yeah. And then so this would be if they were both positive. If they're both positive values, principal stress number 1 is going to be the biggest, and it's going to be positive. And if they're both positive, the difference between would be a smaller circle, but out of plane, there's going to be 0 stress. So that circle would be bigger, and the out of plane would, so this is for out of plane. If they have opposite signs, then sure, then this is going to be, the difference between the two principles is going to be equal to the yield. And so here's your two equations, and I guess this only shows the top part of this equation and then the top part of this equation, because the shear is still this yield tension, this yield normal stress divided by 2 to get that max shear. All right, that was brutal, but let's see. Do you think we could actually figure out the halfway? So if I say my principal stress number 1 is, this is just when principal stress number 1, Oh yeah. So they're using this by knowing the yield stress. So on this, if this is principal stress number 1 and principal stress number 2, I can, if principal stress number 2, that's going to be this, is just 0. So it's just like the picture shows. I'm going to go out on this line to here, and I'm going to get to that point. And then the principal stress is going to equal that yield stress. If I go out the other way, I'm just going to be in compression. Cool. If I pull tension this direction and then this is 0, I'm going to say, yeah, so this is going to be 0 right there, and I'm going to pull tension, and I'm going to pull compression. So it's good even just to, on a graph, get your bearing. And then how about over here? You know what I mean? So if I go principal stress number 1 is positive and principal stress number 2 is positive, hey, I'm still within the confines of this graph, and, you know what I mean? And to get to this confines, I had to say principal stress number, so now I get it. So if so as this picture shows, and if this is the stress that causes those Luder lines to form, the thing yielded. We could get this thing not to yield by doing something. So and that's going to be, and so this is the principal stress number 2 is 0. Principal stress number 1 is going to be a positive sigma y. So principal stress number 2 is 0. We're going to be right here. Principal stress number 1 is a positive y. We're going to be at this value. If I went this direction in the graph and made principal stress number 2 negative, I've failed it. You know what I mean? So that was worse. So if I come back here, and this is going to be a positive, and then I push in this direction, opposite of the Titanic, and Titanic analogy can be either Titanic or going into outer space, even though the vacuum of space isn't that great of ripping things apart. And it'd be theoretically, it wouldn't make sense to be like, well, maybe the center of a black hole. But that's actually compressing. You would need, no, you need a ring of black hole. You need a sphere of black holes around. Yeah, ripping something apart in all directions is a very difficult concept to even, imagine. But vacuum of space, it at least pulls in all directions a little bit. But definitely the ocean's a very good analogy of like things getting hella compressed, but they're not failing. But if this is positive and then this is in compression, then now I kind of see that's gonna, for sure cause failure. So along this positive, and then if this got negative at all. But, if I went out to here and I go positive, I can go all the way up to here. So these 2 points are significant, being like kind of, the most I can do to that thing. So I can pull this direction in a positive, and I can also pull tension this way, the same amount. And it's actually not going to shear about this XY. It's going to shear about the, so the Luder lines wouldn't be visible like this. They would be visible on a side view if the axial tension was equal biaxially. So that's what we have there. Tension and tension. Principal stress, so both those principal stresses are going to be the same. And if both principal stresses are negative values, then same thing. So back up to the picture. If we have compression this way, and then in this direction, compression this way, compression this way, that's very Titanic-ish. But we don't have any compression. We don't have anything going on in this out-of-plane direction, so we're going to get the difference of those divided by 2 is that shear. Sweet. And if we were down here and we moved in any direction by further increasing that negative, then we would have shear. So if this is the most compression, and even in compression, that's cool. I guess I'm learning like exactly why compression is causing failure into shear. I think it's because, it doesn't matter if it's negative shear or positive shear. It's kind of all the same. Heck yeah. I don't think I'll be able to answer from this video, but I was always curious if you could figure out what direction these lines would appear. Is there any rhyme or reason to that? I don't think there is, but I could be easily mistaken. Alright, so I think we thoroughly did it, and we even kind of explained this. But a little bit brutal, but hell yeah. I think that was useful. Like, that was the most studying. I don't think I would have done anything else tonight. So we did it and got a little study session. It's worth posting. So hell yeah, thanks for joining me, and that's a video.